My name is Ahisen Beradin. I am 13 years old and I attend Valley View Middle School in Simi Valley.
My name is Adnan Beradin. I'm 15 years old and I attend Simi Valley High School in Simi Valley. We built a robot for the 2012-2013 FTC Ring It Up season of First Tech Challenge. I'm the team leader of our team, Simi Valley Robotics. This is my younger brother, Ahisen. He's hardware specialist, and we had two other students on the team with us.
We are now going to demonstrate our robot.
During our competition season, we received 3 awards, 1 finalist award, and 2 Rockwell Collins Innovate Awards. We're now going to explain the functionality of our robot. These are the controllers we used during the competition, and this is the laptop we used. It's programmed using a subset of C, Robot C. Generally speaking, the robot is connected using a Wi-Fi router such as this one. Right now it's connected to Bluetooth. This is the NXT brick that we use to run it. It's the main computer behind it. It's made by Lego. These are the controllers for the motors. There is 1 servo controller and 3 DC controllers. These are the servo motors. Underneath are the DC motors.
We have removed the front and top panel for explanation purposes. To drive a robot, we have 4 DC motors at the bottom, which are connected to these 2 DC motor controllers. And now I will show you our mass assembly. This is our mass assembly that is driven by a lead screw attached to 2 DC motors via chain sprocket. When our lead screw is turned, it will push up the second level of our telescoping slide. Because of our string and pulley configuration, by pushing up this level, we can push up every level after that.
This is our bucket assembly. It is used to lift and drop off of rings during the competition. These are what we call the bunny ears. What they do, when we come in with rings, they push the rings against the other rings, thereby causing them to align. Then we just simply move down, pull out, and lock. This lock is run by a servo motor. We use this lock so that when we're driving around in the competition, our rings don't bounce out of our bucket, thereby losing the point. In order to make this bucket angled so that we'll fit on a PVC lip, we had to find some way of angling it. We did this by attaching it to 2 hinges, one of which is controlled by a servo motor. We have 3 positions. Standard position for when we drive around, partially bent position or 45 degrees position for when we're actually hanging the rings, and dumping position to just expel rings if we need to. Every once in a while during the competition, we ran into the problem of misalignment. Before we put side-to-side movement on the actual bucket, we'd have to back out the entire robot and then hang it again. Now what we can do is move to the left or to the right. Then we can simply just hang it. The control for the side-to-side motion is done by this servo motor and this belt. Basically, it just pulls the thing side to side. The entire bucket rides on a piece of Delrin plastic that's also lubricated to give it a smooth flow. The basic of the competition, the basic size of the robot, has to be 18 inches cubed. Because the tallest peg is about 45 inches tall, we had to create the telescoping slide in order to lift the rings up. Now I'm going to show the hanging routine. The routine you just saw is assigned to one button. Basically, it moves the rings down and forward at an equal rate so that it just kind of lightly drops it off and then pulls out. The way we programmed it is by making a subroutine inside of Robot C. You make a block of code, you input what you want it to do, and then you call that block of code somewhere else as many times as you need.
In the last 30 seconds of the competition, we have to lift our Alliance team's robot. Our robot does this by using our already made mass design by lifting up another robot using these forks. These forks were deployed by this latch. This latch is connected to a servo right here, which pushes up these two latches, letting these come out. This is our fork assembly, which we use to lift up Alliance robots. Under it is our outriggers. Our outriggers are used so that we do not tip over while lifting our Alliance's robot. The outriggers stay down by using this lock right here. As you can see, it is quite effective. Let this represent an Alliance's robot. Our forks can lift up to 20 pounds. Due to our outrigger mechanism, it will not tip over while lifting that much. Among other problems, one of the biggest problems we ran into during the competition was our motors burning out because the mast went too far down. It would hit the bottom and the motors would try to spin it and it wouldn't move, which would then cause the motors to exceed their power limit and burn. We solved this by putting a touch sensor and making a software kill. As you can see, the software, it makes it so that it doesn't move down anymore, but it can still move up.